All right, welcome. As we discuss power series here on a technical level, I'm going to encourage you, if you haven't already, to watch the power series motivation video that I have linked prior to this. But whether you have or not, I suppose we can talk power series and talk their convergence. So what is a power series? It's an expression C naught plus C1x minus A plus C2x minus A squared plus C3x minus A cubed and so on. You can think of it as almost like a polynomial centered at x equals A that just is of degree infinity. It doesn't quit, it goes on forever. And so looking in sigma notation, it's probably easier to see this as just some coefficient times x minus a to the n. So the coefficients may be all different, but the a is fixed throughout, and the x is whatever we plug in. Now the thing to think about here is, since a power series is in fact a series, for every x that you plug in to p of x, you will get out a series. Well, series sometimes converge and sometimes diverge. And so the guiding question for us here is, given a particular power series, for what x will the series converge? And so, well, we have to assess the convergence of something with this expression. When I look at this expression, one thing I notice is, for any x that we plug in, x minus a is just a number, and we have a number then raised to the nth power, which is like an exponential factor within our series. But when we had exponential factors within our series, the ratio test was often our tool of choice. So let's see what happens if we apply the ratio test to a power series. So we're going to take a limit as n goes to infinity of absolute an plus 1 over an, which in this case is absolute cn plus 1 x minus a to the n plus 1 over cn x minus a to the n. Now, as we would expect, the exponential factors will cancel quite nicely. The x minus a to the n downstairs and the x minus a to the n plus 1 upstairs will cancel. Well, n of those factors of x minus a downstairs, all of the factors of x minus a downstairs will cancel, and n of the factors upstairs will cancel, leaving one x minus a left over. But if you notice, this x minus a here, which is in the absolute value, we're taking a limit as n goes to infinity, and x minus a has nothing to do with n. So we could actually factor the x minus a out of our limit, and if we did, we'd have the limit as n goes to infinity of the absolute value of cn plus 1 over cn. Now, this is the expression for the limit associated with the ratio test. And when it comes to the ratio test now, I guess, because the thing to think about is here, we could start plugging in different x's here, right? In principle, plugging in different x's would give different values to pop out of the ratio test. Well, we would get convergence from the ratio test if this absolute x minus a times this limit would be less than 1. On the other hand, we would get divergence by the ratio test if this absolute x minus a times this limit is greater than 1. In the other case, we get inconclusivity if the absolute x minus a times limit of n approaches infinity of absolute cn plus 1 over cn is 1. But now, how are we going to make sense of this within the context of our circumstance? Check it out. I want to remind us of something that we invariably have seen previously in our life when studying algebra, but in case we've forgotten it, or just to bring it back to the forefront of our brain, what if you were trying to solve an inequality of the form x minus a is less than r? Now, since the absolute value is small in value here, right, less than r, small absolute value, well, the x that we plug in has got to be close to a. Because if x was a, we'd have absolute value of 0, which is as small as absolute value gets. But on the other hand, absolute value can get bigger from there. And well, the farther x gets away from a, the bigger this absolute value gets. And that absolute value can only get so big in order to solve. So the idea here is, the closer that x is to a, the more likely our absolute value is less than r. And in fact, x can only get at most r units away before the absolute value of x minus a gets too big. And so if you think of a as the center of this interval, then the interval extends in either direction r units. And you go to a plus r and a minus r on either side for your solution. To see an example, what if we had x plus 3 is less than 2? Now here, x plus 3 means that our a is minus 3, and it makes sense here, right, that our center would be minus 3, because plugging in x equals minus 3, that absolute value gets as small as possible. That absolute value becomes 0. And so x equals minus 3 is the center of our interval of consideration. But now, how far can x deviate from minus 3 in order that the absolute value stay less than 2? Well, given that we have absolute value of x plus 3, x can only deviate from minus 3 by 2 units in order to stay less than 2 in absolute value. And so, hey, well, here we go. What if x was close to minus 1? Well, we're still okay. If x was like, minus 1.2 or something, we'd still have an absolute value that would be less than 2. But as soon as x becomes minus 1, now all of a sudden our absolute value is equal to 2, which is, well, not less than 2. And so That's the nature of our solution interval that way. In the other direction, we'd go 2 units away to -5. Now, I tell you, this feels a heck of a lot like a circle, even though that may sound like a crazy thing to say, in the sense that you have a center and that you've got a distance from the center. So you've got a center here at -3, and then you extend like a radius in each direction, 2 units in each direction, to get your sort of interval of interest. Now, why do I bring this up? I bring this up working back to this expression from the ratio test that we cooked up associated to trying a ratio test on our power series. We got this expression x minus a times this number is less than 1. But what if we take this number that pops out of this limit and we divide by it? Well, we'd get 1 divided by whatever that limit is, which is some number. Now, I'm going to call the number that ends up on the right-hand side when we isolate the factor of x minus a, r. And I'm going to use r suggestively because look at the expression here. X minus a is less than r. That takes the exact form of this inequality that we just reviewed. And as we saw when we looked at these intervals, a functions like the center and r functions like the radius, pushing you in both directions. And so in fact, this r that if you apply a ratio test and solve for when the ratio associated with the ratio test is less than 1, and you solve for the absolute value x minus a factor that inevitably results from any power series, that number on the other side of your inequality is what's often called the radius of convergence. Because you see, if we converge when x minus a is less than r, then that r is defining our radius of convergence. If you note, and this is definitely worth sort of keeping in mind, what if we solved in the divergent case? So, oops, I should have this pointing up to the divergent case. So from the divergent case, what if we similarly divide by this limit? Well, then we could say that p of x actually also diverges when the absolute value of x minus a is greater than r. Now, when does that occur? When the absolute value is greater than r, that's when you're further away from your point of interest. So actually, both of these pictures sort of are iconic symbols of what an interval of convergence for a power series looks like. It's always centered around some point. It's always got some radius of convergence that is sort of extending in both directions from that point. And within the radius of convergence, we guarantee convergence by the ratio test. Outside of the radius of convergence, we guarantee divergence by the ratio test. And at the endpoints, unfortunately, the ratio test is inconclusive, which means if we were ever to test these endpoints for a given power series, the endpoints require tests beyond the ratio test. Okay, now I realize it's all symbolic at this point. There's one menial example to just get us familiar with this absolute value inequality, which dates back to algebra. What about the calculus? What about the power series? Let's hammer out an example or two. Let's see this in action so we can see intervals of this form manifesting in the wild, and then we can sort of nail down our understanding of the nature of power series and addressing the question, for what x's do they converge? All right, so let us walk through a power series interval of convergence question. As you can see, my goodness, there's a lot written here, but let's just take it step by step. So here is our power series of interest. We've got sum n equals 0 to infinity of 2 to the n over n, x minus 4 to the n. So we can see straight away, actually, the center of our power series is going to be x equals 4. So we know that our interval of convergence is going to be centered around x equals 4. Ooh, I said interval of convergence. We're going to determine the interval of convergence of this power series, which interval of convergence is just code for all x's for which p of x converges, the very question that was motivating our study today. So if we're going to assess the convergence of a series like this, because, hey, we've got this x minus 4 to the n, this exponential expression, why not use a ratio test? And in fact, when you use the ratio test and set up the n plus 1th term over the nth term, as always, the x minus 4s or the x minus a's in general will cancel nicely. The n factors of x minus 4 downstairs will cancel with n of the factors of x minus 4 upstairs, leaving you with just one factor of x minus 4 upstairs. But fortunately, that x minus 4 has nothing to do with n, what we're taking the limit with respect to, and so that x minus 4 can be factored out. Now, in principle, this x minus 4, plug in different values of x, that could be affecting what x minus 4 times this limit evaluates to. And for our ratio test to converge, we need the limit associated with the ratio test to evaluate less than 1. So we're taking this expression from the limit for the ratio test and setting it less than 1 for convergence, right? So now, we have this expression for our limit that's over here. Actually, we had an exponential expression in the 2 to the n that resulted. Now, ooh, how did I get this? I just took the double-decker fraction that was inside of our limit, and instead of considering the double-decker fraction, keep, change, flipped and multiplied by the reciprocal, however you want to see it. Ultimately, then we get instead of dividing by 2 to the n over n, we multiply by n over 2 to the n. When you see the 2 to the n's, I mean, hey, why not cancel those? And so essentially, we just have 2n over n plus 1 within this limit. But now, remember, the expression we're looking for to be able to geometrically interpret the interval of convergence is of the form x minus a is less than some r. And so what we want to do is take this limit and push it to the other side. Essentially divide this limit to the other side so we have the x minus 4 isolated. Well, to do that, you take the 2n over n plus 1, and whenever you divide, you'd have the reciprocal, right? So by way of division, the 2n over n plus 1 reciprocates to be n plus 1 over 2n. Now this is on the right-hand side, and the left-hand side is just our factor of x minus a, which was exactly what we're looking for. In fact, now this limit evaluates quite nicely, right? Equal heavy rational expression, degree 1 upstairs and downstairs. The limit is the ratio of the leading coefficients, which is 1/2, and that 1/2 is now what is on the other side of x minus 4 is less than, which is playing the role of our r. So I've isolated right here that 1/2 is our radius of convergence, and thinking about that geometrically for our particular situation, x minus 4 less than 1/2 yielding convergence means that we're going to have convergence on an interval that has a radius of 1/2 from a center of 4, which would be an interval between 3.5 and 4.5. Now, if we flip that minus 1 to greater than 1, we'd get divergence everywhere to the right of 4.5 or to the left of 3.5. And unfortunately, we'd get inconclusivity at the two endpoints. I say unfortunately, well, really, that just gives us 2 more chances to show off our series knowledge. So the endpoints of consideration here are 3.5 and 4.5. The ratio test will not be able to tell us what's occurring at the endpoints because the endpoints are corresponding to where the ratio test would equal 1. Well, those endpoints, we got to take them bite by bite with whatever tests are going to work for each of them. I'll take the one on the right as x equals 4.5. So what I'm going to do is literally plug 4.5 into our expression for p to see what the corresponding series is that results. Well, the 2 to the n over n is not affected by what x is, but 4.5 minus 4 is just a half, and so we have a half to the n. And check it out, the half to the n and the 2 to the n will cancel perfectly and give us just 1 over n, that n downstairs will remain, but sum 1 over n, we know how that plays out. That's the harmonic series, and we get divergence. So by the p-test, we would have divergence at x equals 4.5. We mustn't include x equals 4.5 in our interval of convergence because our power series, p of x, diverges when we plug x equals 4.5 into it. What about at the endpoint x equals 3.5? Plug in 3.5 for x, you get 3.5 minus 4, which is minus 1/2. Now here, the 2 and the minus 1/2 still cancel nicely, but for every 2 and minus 1/2 that cancel, you'll get a factor of minus 1. And so here we'd have an alternating series. And remember, when you have an alternating series, all you got to look at, throw the sum away, throw the minus 1 to the n away, do the terms decrease to 0? They do in this case. And so you would get convergence by the alternating series test. So what that says, looking at our interval here, is at the endpoint 3.5, we get convergence. We have to include that in our interval of convergence, whereas the 4.5, we have to exclude that because we get the series to diverge there. So if we were determining the interval of convergence for p of x, our final answer here would be including 3.5 and excluding 4.5, like so. Now, I realize what we just did is a lot, and let me be very clear. Going through one of these power series interval of convergence questions is a lot. But I just want to take a moment to reflect upon what happens if we tweak this just a little bit. What happened if instead of having an n downstairs, we made this n squared? It actually wouldn't change things all that much. We just have an n plus 1 squared, and we have an n squared, which would be what? An n plus 1 squared and an n squared. So here we'd have n plus 1 squared, and then we'd have 2n squared. Okay, but that's fine. When you take the limit here, you'd still get a radius of a half, because upstairs you'd have a degree 2 polynomial with a leading coefficient of 1, and downstairs you'd have a leading coefficient of 2. On a degree 2 polynomial, the ratio of the dominant coefficients for that equal heavy rational expression is still 1/2. So we'd still get actually this exact same picture for the radius of convergence about the center of 4, which means, well, what would happen at the endpoints? So now we got an n squared. Oh, the blue marker bleeds a little bit, sorry. We'd have n squared downstairs, And n squared would mean in this case we'd get convergence via the p-test. What about when p equals 3.5? Now we'd have the n squared downstairs, which means, hey, we'd have an alternating series n squared. Well, actually, that would have to necessarily converge because its absolute series above converges. But even looking at it as an alternating series, throw the sigma away, throw the -1 to the n away, the 1 over n squared still decreased to 0, so we would get convergence there. But if we considered the 1 over n squared, now our interval of convergence would be 3.5 to 4.5, including both endpoints. So what you can see is like subtle changes in the expression of the power series can change the behavior at the endpoints. And for that matter, like if we change this 2, because this 2 was sort of responsible for this 1/2, if we change that 2 to a 3 or something, then we'd end up with a radius convergence of a third. But the long story short is, whenever you are computing the interval of convergence of a power series, first use the ratio test to get yourself an expression of the form x minus a is less than r. That r is your radius, that a is your center. That gives you a picture of what your interval of convergence will approximately look like. But then you've got to dig deeper to the individual endpoints, plugging in the individual x's at those endpoints, because the ratio test is blind to those values of x, and other series tests will be required. But once you pick up the other series tests for those other cases, oftentimes, by the way, in the endpoint cases, you get a pretty straightforward series to look at, then you can say definitively and conclusively what the interval of convergence looks like for your power series, which is essentially defining the domain of that power series, all of the x's for which that power series converges. So with that, let me stop this monster of a video, and we can at least then call ourselves introduced to the ideas of power series and interval of convergence.